All right, welcome to The Explainer. Today we're diving straight into the MIT Quant Bible to pull out the mathematical tools you need to make your best guess when the outcome is anything but certain.
So let me ask you something. How do you actually predict the outcome of a random event? I mean, think about it. From a simple coin toss all the way to the chaotic dance of the stock market, randomness is everywhere. So, how do we cut through all that noise and make a genuinely smart prediction?
So here's our game plan. First, we're going to tackle what I'm calling the prediction puzzle. Then we'll get into this idea of the weighted average bet. After that, we'll uncover a rule that is so simple it's almost deceptive in its power. And finally, we'll learn how to measure the wobble in our predictions.
Okay, let's jump right in. Our first section, the prediction puzzle. The core challenge here is this. We need to find one single reliable number that can somehow represent a whole world of different possibilities.
And look, this isn't some abstract academic question. This is a real daily challenge for quants, for traders, for pretty much everyone. They have to take all these chaotic possibilities, the dice rolls, the market swings, and somehow boil it all down to a single expected outcome. That is the heart of the puzzle we're trying to solve.
So what's the answer? Well, it's a really elegant concept called expected value. You can think of it as our best mathematical tool for placing that weighted average bet on whatever the future holds.
Okay, so what is it? In the simplest terms, expected value is just an average, but it's a smarter average. It gives more weight to the outcomes that are more likely to actually happen. It's the official mathematical way of figuring out what we truly expect to happen over the long run.
Now, the formula might look a little intense at first glance, but I promise the idea behind it is super straightforward. All you do is take every possible outcome, that's your x, and multiply it by its probability of happening, that's the p of x. Then you just add all of those results up. That's it!
Let's make this real with a simple die roll. Each side has a 1 in 6 chance, right? So we just do the math. 1 times a 6 plus 2 times a 6, and so on, all the way up to 6 times a 6th. You add it all up, you get 21 divided by 6, which is 3.5. And here's the cool insight. Obviously, you can't actually roll a 3.5, but that number is the perfect balancing point. It's like the center of gravity for all the possible outcomes.
Okay, now this is where things get really interesting. Expected value has this one property that is so incredibly powerful, it honestly feels like a cheat code for solving some ridiculously hard problems. It's called the linearity of expectation.
And this quote from the source material absolutely nails why it's such a big deal. It says linearity works for combinations of random variables, even if they're dependent. That's the magic right there. It means we can take a huge, messy, complicated problem, break it down into tiny, easy-to-solve pieces, calculate the expectation for each little piece, and then just add them up. And it works even if all the pieces are tangled up and affecting each other. That is a game changer.
So, to see this superpower in action, let's try a problem that seems, well, pretty tough. Imagine a random line of 10 boys and 10 girls. What's the expected number of times you'll see a boy and girl standing next to each other? I mean, if you try to map out every single possible arrangement, it would be a total nightmare.
But with linearity, the solution is just beautiful. We ignore the whole complicated line and just look at one single adjacent pair. The chance that it's a boy-girl pair turns out to be 10 out of 19. That's our expected value for that one spot. Since there are 19 of these adjacent spots in the line, we just multiply that expectation by 19. The complexity just cancels itself out, and we're left with a clean answer, an expected value of 10 pairs. That is the superpower right there.
So, we have our best guess, our expected value. But that immediately leads to the next big question, right? How much can we really trust that number? How much do the actual outcomes tend to, wobble around our expectation? And for that, we have variance. Variance is what quantifies this spread, this wobble. A low variance means the outcomes are all clustered really tightly around the expected value, which makes it a very reliable prediction. A high variance, though, that means the outcomes are all over the place. Now, the math to calculate this wobble looks a little strange at first, but it's really quite clever. We do two things. First, we find the expectation of the outcomes squared. So you square every possible outcome before finding their weighted average. Then, you take the regular expected value we already found, our center, and you square that. The difference between those two numbers is the variance. It's a neat mathematical trick that precisely measures the average spread.
So let's put it all together. The best way to think about it is like firing arrows at a target.
The expected value is the bullseye. It's your best guess, the center you're aiming for. But the variance is the measure of how your arrows actually scatter around that bullseye. It tells you the risk, the uncertainty, the wobble. You absolutely need both to understand the full picture.
So why does all this matter? Because in finance, in gambling, in any field that involves risk, you need both of these ideas. Your expected value guides your strategy. It tells you which bets are good on average. But your variance tells you how bumpy that ride is going to be. Together, they are the absolute bedrock of making intelligent decisions under uncertainty.
So, the next time you face an uncertain choice, don't just ask what you expect to happen. Also ask yourself, how much could this wobble? Because understanding both might just be your own personal superpower.